Alright, so we're looking at lesson 15 today. We're going to look at static, equilibrium, and beam problems. So hopefully after this lesson you'll understand static, equilibrium, and beam problems. The Greek word statos means standing still, and it's our root word for static. So that's where static comes from, standing still. We say that an object is in static equilibrium if it's not moving linearly and it's not rotating. Obviously, the particles inside of the object can be moving, but if the object itself is not moving and it's not rotating, it's in static equilibrium. If a small disturbance of a body from static equilibrium produces forces or moments that tend to return the body to its position of static equilibrium, then the body is in stable equilibrium. So if we touch it just a little bit and it returns to its position of static equilibrium, then that's when we say stable equilibrium. Unstable equilibrium is a state of equilibrium where when the body is slightly displaced, it departs further from the original position. So I've got a picture in just a second that I'll show you of that. And then an object is considered neutrally stable when a displacement will not cause any forces or torques at all. So you can have conditionally stable when a small displacement will be overcome, but a larger displacement will not be overcome. So if you look here, the first cone is in stable equilibrium, because if it's tilted slightly, it's going to go back to how it was. So that's a stable equilibrium. However, the third cone is not stable. It is unstable. Because if you tip it slightly, it's going to fall over. Because currently it's very unstable. It's balanced precariously. And then D is neutrally stable. And that's because it's neither stable nor unstable. A displacement is not going to cause any harm or any forces or torques. The ball's just going to roll a little bit and then it'll stop. So that's when something's neutrally stable. Looking at E, it is in stable equilibrium because if we move the ball just a little bit, it's going to return back to its position. But for F, it's unstable because if we move the ball a little bit, it's going to roll down one side or the other. And then for G, it's conditionally stable, and that's because a small displacement won't affect it. Like if we move it just a little bit, it won't change it. It'll go back to where it was. But a large displacement, if we put it up here, then it's going to fall over. So that's conditionally stable. Now we're going to look at beam problems. The velocity of an object is not changing in any direction, then there is no unbalanced force acting on the object in any direction. So if the velocity is not changing, you don't have any forces, unbalanced forces that are acting on it. An object at rest has a linear velocity of 0 in all directions. So if you're sitting at your desk right now, if you're not moving, your linear velocity is 0. If an object is at rest, the sum of the linear forces in every direction must be 0. Because the linear velocity is not changing. And that's what we're going to focus on today, making the sum of our linear forces in our directions equal 0. So your rate of rotation is called angular velocity, and it is going to change if the object is subjected to a net torque, so a net force. If you have an object at rest, it has 0 angular velocity. If an object is at rest, then the sum of all the torques must be 0 because angular velocity is not changing. So if I have a figure and something is pushing it this way and something is pushing it that way, and the figure is not moving, then that means that they have to balance out. The sum of those torques have to be 0 because it's not moving. It has no angular velocity. But if I erase that one and it starts moving this direction, then that means that it does have an angular velocity because it's rotating. So if you have an object that's not experiencing rotational acceleration, that means that the sum of the moments acting on it has to be 0. So if it's not rotating, then your sums have to all equal 0. And that's going to be true regardless of the point that you choose for your summation. So when we get to our beam problems, no matter where you put the beam, the dot on the beam, if the beam is not moving, everything has to balance out. So let's look here. We have a force of 44 newtons applied to a weightless beam, and we want to find the forces at A and B. So for this one, we have to pick a point somewhere on our beam. And so I'm going to pick A. I'm going to pick this point here. So the force 44 is 3 away from here, and it's pushing down. So that's one that is going clockwise. So we're going to do the distance away from the center and 44. And then we have another force. A isn't a force that we're going to use right now because it is at the center, and so there's not making any change. But B is a force that we will have, and it's pushing up. It's pushing counterclockwise. So it's acting against the 44. And it is 10 away from the center. So 10 times the force of B will have to equal 3 times 44. And so if you multiply 3 times 44, you get 132 equals 10 FB, and divide, you get 13.2. And how many sig figs should we have here? We should have 2, so that's just going to be 13 and then newtons. So that would be the force of B. So now, if you look back at your beam, we have one force that is acting down, which is the 44, and we have 2 forces that are acting up, the A and the B. So 44 is going to have to balance with force A and force B, because the beam is not moving. It is in a static position. So we know that the force of B is 13. So if you solve for the force of A, you should get 31 newtons. And so that would be your answer there. So that's all you have to do for your beam problems. You pick a point. You wouldn't want to pick right here, because that's going to make it more difficult, because you're going to have to pick numbers for here, and then you're going to be using A, B, and C. So you want to pick the point to be on top of a force that you don't know yet, so that you can find the other one and then go back and make an equation later to find the one that you originally put the dot at. But that's all you do for your beam problems. So hopefully that helps you. Your homework is 1 through 20 and the curveball questions, so make sure to do those so we can go over your questions tomorrow.